Welcome to Non-Euclidean Geometry Lesson 6. We're going to talk about triangles in hyperbolic geometry. They're quite different from triangles in Euclidean geometry, as we'll see. One of the equivalents to the parallel postulate is the following statement. The sum of the angles in every triangle is 180 degrees. We know this from high school geometry. But as you recall, we negated the parallel postulate, and therefore we negated all the equivalent statements to that when we defined hyperbolic geometry. So we have that the sum of the triangles in every triangle is not 180 degrees, but we also proved several lessons back that the sum of the angles of a triangle are less than or equal to 180 degrees. And if you recall, that theorem applied to both Euclidean and hyperbolic geometry. So between the two statements here, the negation of this statement here and this theorem that we have here, the only conclusion is that the sum of the angles of a triangle is less than 180 degrees in hyperbolic geometry. We also have the following theorem, which is even more surprising. There are triangles with angle sums arbitrarily close to 180 degrees, but not equal to it. And we'll show that in the next slide. Let's prove the theorem from the previous slide that we can get arbitrarily close to 180 degrees for the sum of the angles in a hyperbolic geometry triangle. First, let me mention that the angles along a straight line, for example, this angle here, EAC and CAB, this angle and this angle, they add up to 180 degrees. That's true for both Euclidean and hyperbolic geometry. So keep that in mind. Now, in terms of the proof, to take any triangle A, B, C, and pick a point D that lies between A and B. As D approaches A, so as we move this out here, the angle ADC, so this angle here, gets closer and closer to this angle here, EAC. And the measure, as we move D this way, the measure of ACD, in other words, this angle up here, ACD, this goes to 0. Thus, the sum of the angles of the triangle ADC can be made arbitrarily close to the measure of EAC, that's this angle here getting closer to this, plus CAB, which we're not altering, and these two together equal 180. So we can get as close as we want to 180 degrees for the sum of the angles in the triangle ADC. Okay, so that's our proof. The following theorem implies that there are no squares or rectangles in hyperbolic geometry. So here's our theorem. The sum of the angles of a simple quadrilateral, in other words, a four-sided figure, non-self-intersecting, so you don't have any of the edges intersecting themselves, another edge, is less than 360 degrees. So consider the quadrilateral on the left of the figure below, so this one here. Draw a line to dissect the quadrilateral into two triangles, as we've shown here. So we've dissected from the by connecting two of the vertices with this dashed line. Then by theorem 15, the angle of delta plus alpha sub 1 plus beta sub 1, in other words, these three angles, are less than 180 degrees. And then these three angles here, gamma, alpha sub 2, beta sub 2, those add up to less than 180 degrees. And if we add these two things together, we're going to get delta plus gamma, and then these two add up to alpha, and these two add up to beta. So we get the sum of these four angles in the quadrilateral being less than 360. So that's the proof of this theorem, and I just made a note here. A similar dissection in the two triangles can be performed for any simple quadrilateral. So you can, move this around a little bit here and get different shapes, but the same idea is the same principle of dissection is going to work. In Euclidean geometry, similar triangles can be of much different sizes. We could have one equilateral triangle, for example, that's the size of a coin, and another equilateral triangle that's the size of the solar system. In hyperbolic geometry, this isn't possible. We have this theorem: if the angles of two triangles are equal, then the triangles are congruent, meaning their respective sides are equal. So that's the case in hyperbolic geometry. You can have similar triangles that are actually always congruent. They're the same size, and we'll prove that in the next slide. To prove the theorem, let's assume that A, B, C, and A prime, B prime, C prime are similar, and that A prime, B prime, C prime is the larger of the two. And then we'll get a contradiction, which will force us to conclude that they're congruent. So assume that AB is less than A prime, B prime, and that AC is less than A prime, C prime. So this is less than that. Then select D on A prime, C prime, such that A prime D is equal to AC, and do the same on A prime, B prime. Select an E such that A prime E is the same length as AB. And we know that E is between A prime and B prime because of the assumption we made up here, and the same thing for D. Then we use the side angle side triangle congruence principle, and we have that A, B, C, so this triangle here, is congruent to A prime, E, D, since we have this side is equal to this side is equal to this side, and then by similarity, that was the assumption of our proof, that the angle at A is the same as the angle at A prime. So this triangle here is congruent to this triangle here, and then we can conclude from that ACB, so ACB, the angle at C here, is equal to A prime DE. So this angle here is equal to this angle here, and then this angle here, ABC, is equal to A prime ED, this angle here. Now what we want to do is show that this quadrilateral has angle sum 360, and that'll be a contradiction. So let's see how we can prove that. Since A prime DE, this angle right here, plus EDC prime equals 180, and A prime DE equals C. In other words, this angle here equals this angle here. Then we can just substitute in C for this here, and we get EDC prime plus C prime. So in other words, the sum of this angle and this angle is equal to 180. And similarly, the angle DEB prime plus B prime, the angle of B prime, is equal to 180. And then that gives us that the quadrilateral DEB prime C prime has sum of its angles equal to 360. But we showed for hyperbolic geometry that the sum of the angles of a quadrilateral is less than 360 in theorem 17. Thus, our assumption here that we started with is false, and we could have gone in the other direction. Of course, we could have assumed that ABC was bigger than A prime, B prime, C prime. That's equivalent. So we're not going to do that. But so that our only conclusion is that A, B this length here equals A prime B prime, and AC, this length here, equals A prime C prime. And then we have the triangles ABC and A prime B prime C prime are congruent by the angle side angle congruence principle, which is what we wanted to prove. The deficit of a triangle is the amount by which the sum of the triangle's angles is less than 180. Using this terminology, we can restate theorem 16. Recall that was earlier in our lesson. There are triangles with deficits arbitrarily close to 0. We also have a result here. If we take a triangle ABC and we divide it into two triangles going with the line going from a vertex to an opposite side, it turns out that the deficit of the overall triangle equals the sum of the deficits of the smaller triangles here. We can see that. We just write down the different deficits here. The deficit of ABC is alpha plus beta 1, beta 2 plus delta. And the deficit of this triangle here, ABD, is this. And the deficit of this triangle here, we'll call that D2, is this quantity here. Then if we just note that gamma sub 1 plus gamma sub 2 is a straight line, or is on a straight line, that equals 180. We add these two quantities together and we get this. We'll keep the two gammas together because we know they're 180. And we subtract that from here, and then we see the result is the same as the deficit for the overall larger triangle. So in general, that's true. If you take a triangle and do a dissection from a vertex to an opposite side, the sum of the deficits for the two smaller triangles equals the deficit of the larger triangle. We can also take a point in the interior of a triangle, as I'm showing here on the left, and then the triangle is formed from joining to this point, this triangle here, ADB, DBC, ADC. The deficits of these three triangles add up to the deficit of the overall triangle here. We can show that in this slide here. So what we do is the first step is we take this figure and then we just extend the straight line from B through D down to AC, and it intersects here at point E. And then we just write down the various deficits. So the deficit of ABC, using this these two triangles here, A, B, E, and C, B, E. So in other words, the one on the left and the one on the right, we have this here. And then we can write down the deficits of the smaller triangles, ABE, ABE. So that's in terms of this triangle and this triangle here. And we already know what that is from the what we proved on the previous slide. It's the sum of the deficits of ADB and ADE equals the deficit of AEB, which is what I wrote here. And then we can do the same thing on the right. So the deficit of CBE is the deficit of this triangle plus the deficit of this triangle. So I wrote that here. And then we note that the deficit of ADC is the sum of this deficit of this triangle and this triangle here. And then we can just put everything together. The deficit of ABC is the sum of the two deficits here, ABE and CBE. So in other words, the left side and the right side, the deficit of those two. And then we plug in these here. So ABE, we plug in ADB plus ADE. And then we plug in for the deficit of CBE, this here. And we group these two together because of this identity we noticed over here. And then we just plug that in and we get the deficit of ABC equals the deficit of ADB, plus the deficit of ADC, plus the deficit of CDB. So we've proven that you can pick any point inside of a triangle, and the deficits of the three triangles formed from joining to that point in the interior equals the deficit of the entire triangle. So in general, we have the following theorem. If a triangle is subdivided into other triangles in any manner, then the sum of the deficits of the constituent triangles equals the deficit of the given triangle. Okay, so we proved a couple of parts of that. We didn't prove all the possible cases, but in general, this theorem is true. Then moving on to another topic, which I just squeezed in here on this slide here. In Euclidean geometry, the sum of the internal angles of an n-sided polygon is equal to n minus 2 times 180 degrees. You can look that up if you like in the Wikipedia article Polygon. In hyperbolic geometry, we have something similar but slightly different. The angle sum of an n-sided polygon is always less than n minus 2 times 180 degrees. This follows from theorem 15, which we proved earlier, or stated earlier, and the fact that a simple polygons whose sides do not intersect, can be decomposed into a collection of non-overlapping triangles. So I'm going to state that on the next slide in terms of a theorem. Theorem 20 is a restatement of what I mentioned on the previous slide. The angle sum of an n-sided polygon is always less than n minus 2 times 180 degrees. We have a proof. Divide the polygon into triangles as follows. Any polygon with n sides, also known as an n-gon, can be triangulated by drawing n minus 2 diagonals from one vertex to all the other vertices. This effectively subdivides the polygon into n minus 2 triangles. And I have an example here where you have a 7-sided figure. So you pick one vertex and you draw lines to the other vertices. And this, so you have 7 sides here, and you get 1, 2, 3, 4, 5. So n minus 2 triangles. And then we're almost done. Since each triangle has an angle sum of less than 180 degrees, we mentioned that before, the sum of the angles for the n minus 2 triangles in the triangulation of the n-gon must be less than n minus 2 times 180 degrees. However, the sum of the angles in the triangles equals the sum of the angles in the n-gon. And so the sum of the angles in the n-gon must be less than n minus 2 times 180 degrees. And you can see that here. The angles in the n-gon, of course, are these vertices here. And if you look at all the angles from the triangles, this one angle here of the polygon makes use of all 5 of the triangles. Then this vertice of the polygon makes use of just one angle from one triangle. Then the other ones are just, you have to add up an angle from 2 different triangles to get the corresponding angle for the polygon. But they all match up, and so the sum of the angles of the triangles and the sum of the interior angles of the polygon are the same. And so we have our proof. On this slide and following, we're going to talk about the relationship between a triangle and an associated secure quadrilateral, which I'm going to construct one example on this slide here. So we have a triangle A, B, C, this here that I'm outlining. Let's take, and it's obtuse, so we can do a different example when all the angles are acute, but in this case, the angle at B is greater than 90 degrees. And so what we do is we take the midpoint between A and B, that point E here, and then we take the midpoint between A and C, it's the point G. Then we draw a line between E and G. We just extend the line out here. And then for each point in the triangle, we drop a perpendicular down to this line EG. So you see from A, we draw a perpendicular down to EG, and it intersects at the point D. And then from B, we draw a perpendicular upwards towards the line EG, and it intersects at F. And then finally, we draw a perpendicular from C to the line EG, and it intersects there at H. So we have these three right angles. Then we're going to make use of the proposition 26 of Euclid's Elements. That's the angle-side congruence. So you notice here, let's look at the triangles A, DE, and BFE. So this triangle and this triangle here. So we have an angle here. These are both 90 degrees. And then, of course, this angle here and on the other side of it is the same. And then we have this side here, AE is equal to EB. That was the way we constructed it. So in other words, a triangle ADE is congruent to BFE from the angle-angle side congruence principle. And that means that these two are congruent. And then we can do the same thing between ADG and CHG. You notice they both have a 90-degree angle, and then they have this angle here on either side of G that they share, and then AG is equal to GC. So ADG is congruent to CHG, and from that we can conclude that AD is equal to HC. So we have AD is equal to FB, and is also equal to HC. In other words, FB is equal to HC. So these two lines are the same. We have a right angle here and a right angle here. So BFHC is a Sakiri quadrilateral. The base, it's kind of turned upside down. The base is FH, and the summit is BC, and the two arms are BF and CH, and they're equal in length. And we can do a similar analysis to the other sides of A, B, and C. So we did it for BC, but we could do it for AB and for AC, but I'll just show you the one example here. So again, this was done when we had an obtuse angle in our triangle. I'll give you a different example on the next slide. Let's do a similar analysis to what we've done in the previous slide for a triangle ABC that has all acute angles, as shown in the figure. So A, B, C, all the angles here for A, B, and C are less than 90 degrees. And we can develop the Sakiri quadrilateral in a similar way. We pick E to be the midpoint between A and B, and then G to be the midpoint between A and C. And then we draw a line between E and G, extend that. And then for each vertex of the triangle, we drop a perpendicular to the line EG. So you can see here we have a perpendicular from B, another one from A, and then another one from C. And the points of intersection are D, F, and H respectively. And then we can show that this triangle here, AEF, is similar to DEB by the angle-angle side as we did in the last slide. And then from that we can deduce that this side here, AF, is equal to DB. And then we can show that this triangle AFG is congruent, to GHC, again by angle side. And then we have that AF is equal to CH. And since AF is equal to both DB and HC, we know that DB and HC are equal, and that gives us our Sakiri quadrilateral upside down. So the base is DH. We have the two right angles here, and then the arms DB and HC are of equal length, and then the summit would be BC. We could do the same thing if ABC was a right triangle. Then A would just kind of move directly over here, and it's even easier to do the construction. I'll leave that as an exercise to the reader, but I won't actually do it here. I also have this dotted line in here, which I'll make use of later, but it's not relevant to the discussion on this slide. Based on our work from the last few slides, we have this theorem. The sum of the angles of a triangle equals the sum of the summit angles in each associated security quadrilateral. We'll do this for one case where we have a obtuse angle here at B. Recall this is the diagram from a few slides back. And what we want to show is the angle at A, B, and C. The sum of those three angles equals the sum of the angle FBC and HCB. In other words, the sum of the two summit angles here. So the first step is we'll have this preliminary result. We'll take HCB, we'll break that into two angles. This angle here, let me draw it in. So this angle here, and then this angle here. Let me put a little dash here. So this angle here, as you recall from before, that was the same as this angle up here. So just writing that out, we have HCB equals GCB plus HCG. So GCB plus HCG, excuse me. And then we carry over the GCB, but then we replace HCB with this angle up here, which is GAD. Then we carry the GCB over again, but then we break up GAD into two angles here, DAE, and then GAE, this angle here. And then we make one more replacement. We have DAE. So this angle here is the same as this angle right here that I'm pointing to, which is EBF. So we have this preliminary result. Now let's add up the two summit angles, FBC, and HCB. And we'll plug in HCB, this result that we got for HCB in here. And then we'll associate this EFB with FBC. So FBC and EBF. So those two together, put those two together, and then we'll just carry over the GCB and the GAE. Okay, and then these two together, these two angles added together are EBC. But what is EBC? That's the angle at B. And then GCB, just carrying this over, GCB is the angle within the triangle at C. It's this angle right here at C. And then GAE, that's the angle associated with the vertex A of the triangle. And so we've shown that the sum of the two summit angles is equal to the sum of the angles at each vertex of the triangle, which is what we wanted to show. So it's just one of several cases, but just to give you an idea how the proof goes, it's pretty similar in the other cases. Using some of the results that we proved earlier, mostly in lesson number 3, concerning security quadrilaterals, we have the following theorem. It comes in 3 parts. The line joining the midpoints of two sides of a triangle is parallel to the line containing the third side. has a common perpendicular with it, and the segment joining the midpoints is less than half of the third side. So let's look at a proof here. The line joining the midpoints of the two sides of a triangle is parallel to the line containing the third side, since the summit and base of the corresponding security quadrilateral are parallel by theorem 3. So this is from our construction. When we built the security quadrilateral for a triangle, the base was actually the of the quadrilateral was the line going through the midpoints of two of the sides, and then the other side of the triangle was the summit, and we know that those two things are parallel from theorem 3. And then from theorem 2 we get the second part here. The line joining the midpoints of the two sides of a triangle has a common perpendicular with the third side, since the summit and base of the corresponding security quadrilateral have a common perpendicular. That was theorem 2 from lesson number 3. So what we're left is the third part here. The segment joining the midpoints of two sides is less than half of the length of the third side. We'll prove that on the next slide. We're going to prove the third part of the theorem for the case where we have a triangle ABC where B is obtuse. The other two cases where all the angles are acute, or where you have a right triangle or similar. What we want to show here is that EG is less than half of BC, where E is the midpoint between A and B, and G is the midpoint between A and C. So we want to show that this line connecting the midpoint of two of the legs of the triangle is less than 1/2 the third leg or edge of the triangle. So first we note that FH here, that is equal to DH minus DF, and then we can write DH as DG plus GH, which I wrote here, and then DF we write as DE plus EF, which I've written here. And then we make use of the congruent triangles that we proved earlier. So ADG is congruent to CHG, and that means that DG is equal to GH in length. And then we had this triangle here, ADE and BFE are congruent, and that means that DE equals EF, DE equals EF. And then we just plug these two equations in here, and we get that FH is equal to 2DG minus 2DE. You can write it like this. And DG minus DE, DG minus DE is equal to EG, and that's the segment connecting the midpoints. So we have this, and we can write that as EG equals 1/2 FH. So EG, the line connecting the segment connecting the midpoints, is equal to half the base of the security quadrilateral associated with our triangle ABC. But we know from theorem 7 that the base of a security quadrilateral is less than the length of the summit BC. So that gives us that EG is less than 1/2 the length BC, which is what we wanted to prove. Okay, so that's the last slide in this lesson, but I have quite a few more lessons which I'll be posting as I complete.